Welcome to our worship facility webinar, How Loudspeakers Can Help Challenging Church Spaces with Dale Shirk, sponsored by Biamp. I'm Gene Lass, editor of Worship Facility. Dale, why don't you get us started?
Thank you, Gene. I'm Dale Shirk. I've been with Community and now Biamp for about 6 years. Prior to that, I was had my own installation contracting firm of about 25 years. I had my own, and a few years before that, I worked for some others. So I've got extensive experience in loudspeakers in churches. I did mostly church jobs in my business. So let's get started. How loudspeakers can help challenging church spaces. The main challenge: achieve good intelligibility for everyone. If the spoken word is not heard, then we haven't accomplished our job. Basic acoustics. Inside a building, sound will bounce off of surfaces until it's entirely absorbed. The surfaces which are porous or lightweight will move easily, will absorb sound. The sound, basically just the moving air, rubs against porous material. Friction changes the energy to heat. Surfaces which are hard, smooth, and massive will reflect sound. So that would be, masonry and so forth, concrete. Larger spaces will have longer path lengths, which means sound travels further and takes more time to hit enough surfaces to be absorbed. Even though the sound disperses with distance, 6 dB per doubling of distance, that energy simply goes in other directions. It doesn't go away. It's still contained within the room and has to be absorbed by a surface or by the air itself before it will die away. We call that sound that hangs on reverberation. We're familiar with that. Reverb time, or RT60, is the time in seconds for a steady sound once the source is stopped to fade down 60 dB. In practice, we might measure that at 30 dB and double, whatever, but that's where the term comes from. Terms like live and wet indicate a lot of reverberation, while dead or dry indicate little reverberation. Reverberation time alone is not the only metric needed. Room volume also comes into play in determining the reverberant level and interference to intelligibility. As an example of that, a boardroom that RT60 of 2 seconds would be considered extremely live, while the same 2 seconds of reverberation in an arena, in a hockey arena, for instance, would be considered very dead. So it's not just time, it's time and volume. In a large room, large live room, the reverberant sound is close to the same level everywhere. So no matter where you move around, the reverberation is the same because it's bounced all around the room before it got to you. If a RT60 is 1.5 seconds or less, there will not be reverberation-related intelligibility issues in a medium-sized house of worship. For an RT60 from 1.5 seconds to 2.5 seconds, you do need to be a little careful to cover the audience evenly and not spill excess sound on the walls and ceiling. Longer reverb times, longer than 2.5, 3 seconds, we get into where we have to kind of carefully engineer it, modeling it in a 3D program where you can evaluate the surfaces. You build a computer model with each surface and you evaluate how the sound travels around in that room. That takes much more time and more information about the room, the materials, exact dimensions. May require getting a consultant involved to get into that depth of modeling. Acoustics basics, intelligibility. We measure speech intelligibility, or I should say predict speech intelligibility, with what's called speech transmission index, or STI. And that is in turn calculated from modulation transfer function. Modulation is the this graphic on the left here is a sentence of speech. Modern electroacoustics began in 1915. You see my mouse there, Gene? Is that
Yeah,
visible? Okay, good.
yeah.
So this first word, modern, that cut there is the D when we close off the air, modern. So in order to hear that D, we need to hear that there was a lot of sound and now there's no sound. When we add reverberation to that same signal, it fills in the gaps and makes it very difficult to hear that sound. So the modulation is the large signal, small signal, going back and forth between large and small. And noise would be a continuous level across there that kind of fills in the low parts. Reverberation is, of course, related to the high parts. The higher the sound, the more the reverberation fills in. So you can't overpower, you can't just turn the volume up. You can turn the volume up to get ahead of noise, but not reverberation. And unfortunately, I don't have those tracks saved as a audio file in this slideshow, but if you'd hear it, you'd understand that's how the reverberation fills in those gaps, and we can't hear the little ticks and clicks that make speech intelligible. So STI is a rather lengthy measurement to gather. So there's a shortened version of it called STI-PA, Speech Transmission Index for Public Address. And it gives the same information, it just gathers it in a sort of a simpler statistical way to get a representative sample. And it's scaled from 0 to 1. Typically, we'd like to see, churches be in the 70 to 75 range at least. If the worst seats are down at 60, that's passable. But so if you hear people talk about STI, that's scale. That's what we're talking about. The evaluation of STI is dependent on RT60, reverberation, and later rivals, echoes. Frequency bandwidth of the transducer or source, background noise level, spectral content. It's in general for speech intelligibility, the direct sound should be 10 to 15 dB more than the background noise. 25 would be ideal. Above that, you don't gain much. And it's also the dBSPL at the point of observation. Louder is only better to a point. This is something people don't understand. You can't just keep turning the volume up to get more intelligible. At about 80 dB, STI-PA starts decreasing at 80 dB, primarily as a function of how the human hearing works. Essentially, this is the human ear's compression threshold. Those, if we remember that speech signal, the loud parts would be compressed by the ear, and now we don't have as much modulation anymore. We lose some of that depth, which carries intelligibility. Additional intelligibility issues, echoes. Echoes can come from rear wall, balcony front, concave architectural features, anything that's curved inward that would focus sound back to a point. And again, for an echo to be heard as an echo, there's a number of things have to happen. It's dependent on where the source is and where the listener is. The echo doesn't necessarily return back to the source. We're interested in echoes that are sourced where the loudspeaker might be, and does it return an echo to where people will be listening? An echo that goes up into the ceiling doesn't matter. It can just go up there and go away. That's difficult to assess offsite from pictures. We can look at pictures and go, well, that may be a problem. It may not. We may not quite know what that surface is. So that often has to be assessed in detail on site. If you want to study solutions, that requires 3D modeling, again, to see what surface is actually causing the problem. and what can be done about it. It almost always requires acoustic treatment solutions, absorption, just soak the sound up that's hitting that surface, diffusion, scatter it instead of a flat surface, make it curved, or simply angle the surface in another direction so that the echo goes off where people can't hear it. Other issues that might affect intelligibility, distortion, obviously if you've got clipping or other distorting problems in your sound system, that'll affect intelligibility. Frequency response problems, if somebody put a big smile on the equalizer that's all bass and high frequencies, none of the important mid-ranges are coming through, well, then that's going to be a problem. And noise, and that noise can be through the system or, HVAC, whatever noise in the room can affect intelligibility. So a little bit of very, very basic stuff about loudspeakers, directivity. Which direction is the sound going out of it, and does it control the sound? A larger horn system will try to control the sound, not let it go everywhere. We want it to go just where the audience is. And that's specified as 6 dB down coverage angles. Horizontal coverage, vertical are separate. Actually, it's a whole 3D thing. We just simplify it to horizontal and vertical. Over what frequency range does it control the direction of sound is going? For a given frequency range, and you want a narrower coverage, will require a larger physical dimensions. Likewise, for a given coverage angle, to maintain that angle to a lower frequency will require large dimensions. So in this case, size matters. It's about angles and frequencies. What frequency can we control? If we have a small device with just a small tweeter and no horn, well, those high frequencies are kind of going to go everywhere. You have a large horn with large sound walls, a large mouth area, a lot of control where the sound goes really well. The basic idea is that the loudspeaker should aim its direct sound toward the ears and not toward the walls, not toward unoccupied areas. And that's simply because all of the sound out of the loudspeaker contributes to the reverberation, but only what gets to the ears is the direct sound that we hear, that we get the intelligibility from. So if we're putting extra sound on the walls and ceiling, that's not good. That'll create a higher perceived reverberation and less intelligibility. The direct sound from the speaker should be the same level in all occupied areas. This is kind of job one, and in some ways the hardest thing to accomplish. Is remember, the reverberant sound in a live room is kind of the same everywhere. So we want the direct sound from the loudspeaker to be the same everywhere. This gives similar intelligibility, oral experience for everyone. By eliminating hot and cool spots, the average intelligibility over the whole room is better for everyone.
That's the idea of even coverage. So everyone in the seats can hear the same quality.
Yep, absolutely. So which speaker to use? Well, when you first look at a speaker, the speaker will tell you what its preferred tilt angle is. Now, let's just look at these two for a minute. Here we got us on the top left, we have a 60-degree vertical angle. The green area is masked to plus and minus 2 dB. I think this is A-weighted SPL. This little black line here represents the audience. Everyone along this black line is within that green area, so within plus minus 2 dB coverage. If we were to tilt this speaker at a shallow angle, we'd get a hot spot in the middle. If we were to do a steeper angle, we could get even coverage, but this wouldn't be as large an area. So this is kind of the largest area we can draw. We always aim the speaker at the furthest, or at or near the furthest listener. So a speaker has a large vertical angle. It's going to want to be tilt down a little steeper. Down here in the bottom, we have a narrow speaker, actually a little column speaker with a 15-degree vertical pattern. And here again, we got a very long area within the green, but only if that's at a shallow angle. If that were a steep angle, it would punch a hole in the middle and miss the front and back. So you need to understand your speaker and where it, how its directional angle will tell you what its most effective application is in terms of tilting it down. Wider horizontal dispersions generally cover more floor area. In this case, this is a 60 by 60 and same size area, same model speaker, only with a different horn pattern of 120 by 60. They still have the same vertical, but you can see where this covers a much larger area, mostly within the green, a few hot and a few cool spots. But this one just punches a big bright hole in the middle, and that's simply the horizontal. It's going to want to cover a smaller area because of the narrow horizontal angle. Where to locate the speaker? Well, obviously in front of the listeners. Point it so that they can see, you can't hear what you can't see. Well, you can. You need to be able to line of sight to the speaker. Locate such that the loudspeaker sound comes from the same general direction as the acoustic sound of the sources. Obviously, we want the direct sound toward the front of the room. That's where someone's talking. It sounds like it's coming from there. It's more natural, and we soon forget that it's actually coming out of a loudspeaker, not the person talking. We need to locate it where there's suitable rig points or building attachment provisions. Obviously, we can't necessarily hang it everywhere if there's no attachment, or we may need to provide, some reinforcement in the attic to create a space, a hang point for a speaker. Beware of visual sightline issues, video screens, stained glass, other visual elements. Do not put your big black speaker directly in front of the face of Jesus on the stained glass window. Even if it's only from the balcony, that will not pass muster. You like that, huh?
Yeah, that's good. That's a good graphic.
Where to locate the speaker? I've said before, aim the speaker at or near the furthest seat it is intended to cover. If the front's too loud, try raising the speaker up and a steeper tilt angle. And don't forget about the roof. If you're doing this in a 2D modeling program, you might find, hey, this is the perfect height to hang the speaker, and then you realize it's 10 feet above the roof. It won't work. Or if the front's too loud, use a smaller vertical angle speaker. If the front's too quiet, and the reason I'm saying the front, the back half is easy to cover right because it's far away and it's very little difference in distance and angle. So covering the back of the room is easy. Getting the front to be the same is the difficult part. If the front's too quiet, lower the speaker, use a shallower tilt angle, or just use a larger vertical angle to get more down front. And again, when you're lowering the speaker, beware of sight lines. You can drop it down till it gets in front of the projectors or whatever. Using fill speakers. Well, first try a little harder to get the good coverage from the main speaker. A single source is always best if you can possibly do it. Typically, the front corners of a rectangle room are going to need coverage. In this case, here we have a main speaker covering the audience, and we got this little corner up here that's being missed. So try to keep the sound going in the same direction. You can add a fill in the corner and come across. That'll fill that area, but it's going to cause arrival time problems out in the middle of the room. If we put a small fill speaker going this direction, it's kind of still moving outward from the front, we won't create problems in other areas as quickly. If possible, reduce the throw distance from the fill speaker to the filled area. Just simply a small speaker closer, run quieter. Will have less detrimental effects in other areas. Only fill the frequencies needed. The main speaker will have enough low frequency spill because low frequencies kind of go everywhere. You only need to add mids and highs, and then delay the fill, even if it's right next to the main speaker. And this is a little more complex topic, I guess, in commissioning a system, but try not to. You may want to intentionally misalign the two speakers so that they're at least 2 wavelengths out of alignment at the lowest frequency used by the fill speaker. And the reason is that will result in narrow notch comb filters, not the wide. The first notch is an octave wide and much more detrimental. What about stereo? If you do stereo, each channel should cover the entire audience. You should maintain no more than 20 milliseconds arrival time difference between the adjacent channels. That's so that we don't hear an echo. If we have, there's something that's in both speakers and it gets out 30, 35 milliseconds, you start to hear at 30, you won't hear it as a distinct echo at until you get out to about 50 milliseconds. But at 30 milliseconds, it can totally trash the intelligibility. So it kind of limits you to about 20 milliseconds, which limits the width, how far apart the speakers can be. It also favors higher loudspeaker trim heights because the higher you are, the less delay you get as you move off to the side.
Mono versus stereo is a big debate for a long time. Do you think that stereo would then be more ideal for a church where it has the worship band, the full rock and roll church, as they say, rather than maybe a smaller church where it's a pastor and a piano, or a pastor and a guitarist, or something like that, where you have more things to mix? Would you be better with 2 or 3 channel stereo than you would have a more simple church production?
Yeah. In fact, this is what I'm actually getting to right here.
Oh, well, we're on the same wavelength then.
No.
Yeah.
A 2-channel stereo will not provide the phantom center image that you get in a home, in your living room system, and that's why people. Well, you can't do stereo PA; it doesn't work. Well, it doesn't work the way it does in the living room, but it still works. It still can provide useful spaciousness, and it's actually relatively inexpensive in a narrow room. The fill speakers I talked about, 2 mains instead of a main and 2 fills, can end up being very close in price. Now, if you really want to do it right, 3-channel stereo, LCR, and that stands for left, center, right, that will provide the firm center image. That's stereo was originally invented by Dr. Snow in the 30s at AT&T. Was meant to be 3-channel. It was simplified to 2-channel just to save cost. We've been listening to 3-channel stereo in movie theaters for several decades now. The speech is in the center, the music and effects are in left and right. So a 3-channel system, you can do spacious, musically optimized left and right, where the center is more speech and clarity optimized if you wish to go that way. Higher cost, obviously a console with LCR panning now. Nowadays, most middle range and better consoles, that's just a digital consoles. That's just a click in the setup screen. You can create LCR panning. Back in analog, that was a whole different console that you needed to do that. It can be used in wider rooms without violating the arrival time difference because we're only ever panning from left to center or center to right. We're never putting anything in left and right, but not center. So, and it's 3-channel stereo is actually easier to mix because not only do we separate instruments from each other by by their frequency content, and level, we can also by direction. We have one guitar on the left and one guitar on the right. They're not walking on each other because we can separate them by our ears hearing which way the sound's coming from. So it is easier to mix in 3 channels than it is in 1 or 2. So building types and the sound system. This is traditional shoebox, kind of what I showed you before. Overhead front center speaker and a pair of fills filling in the front corners. Very simple. Or the alternate is left and right stereo. This could be covered with 2 speakers, and this speaker will cover well enough to the opposite side so both can be heard the whole way across, and not need any fills because things like speech are in both, and you know, it covers all the area. They can be mounted high like a point source, or down low, a column line source on the post on the wall. Wide fan or diamond shaped room. This is an exploded cluster. This is sometimes misnomered LCR because there's a speaker on the left, speaker in the center, and a speaker on the right. But they're actually intended to cover their own area, not be a stereo system. In fact, in a wide fan room like this, stereo is extremely difficult to do. So don't confuse LCR with a 3-channel exploded cluster mono system. Another common building type, the cruciform or cathedral cross-shaped in plan view. These are typically traditional, very reverberant space. Column speakers, line source speakers on the wall are often the best here, and we'll show why shortly. Again, with transepts, we've got seating off in the corner, so we'll need a separate speaker covering those as well. A long, narrow church can often be covered from the side, left and right from the sides. You could, if the reverberation is, the room is dry enough, not too reverberant, you could hang a speaker in the center as well. Either way. And again, because they're narrow, they work well to be driven in stereo and get the spaciousness. In this case, we've got balcony over and under that will need to be filled, need small fill speakers in that area as well. So let's look at a couple of particularly difficult church spaces on opposite ends of the spectrum. On the live end, we've got the traditional cathedral. And there's a little math for you. Large cubic volume plus hard surfaces equals long RT60. And long reverberation equals intelligibility issues. How to deal with that? For traditional worship, the music is generally acoustic. Choir and organ heard in the room without reinforcement often, or other simple concert instruments that can be, you know, heard throughout the room. That the room supports sound really well. It's just, in some cases, you might say too well. Every little thing can be heard everywhere. The room size in RT60 may dictate the music speed. That's why some of your classical styles are very slow, because you can't change chords quickly. If the sound is going to hang on for 4 or 5 seconds, it's going to mush one into the next. So you've got to, you know, make your changes slowly and give them time to settle in. Speech reinforcement. Again, for best intelligibility, we like to use a line source. In this case, I'm not trying to push my brand over others. I mean, other manufacturers have similar things, but this is an emphasis. It's the line column, line source. It's got a lot of small speakers, and they're all driven equal level. In this case, there's 2 of them. That's about a 7-foot high, tall column, and it's projecting sound. This is, I don't have to took the scale off, but it's about 80 feet to the back. And I'm I'm showing the audience area as this dotted line is all within that green. Hey, remember that green was plus and minus 2 dB. So by tilting this slightly mechanically in the case of our speaker, it could be digitally steered, in which case it's tilted electrically. But when you take this beam and put the audience right along the edge of the beam, we get even coverage from front to back. Obviously, the height is very important. A couple inches one way or another matters here. And we've got a total tilt of 3 degrees, maybe between 3 and 4. So that this beam meets the back is, again, very, very highly dependent on precise amounts of degrees. Half a degree makes a difference here. And obviously, this wouldn't work on a steeply sloped, a sloped floor. You couldn't do this application at all. But the idea here is that all the sound stays down here low. It doesn't go up into the high space where the ears aren't. And that's the key to getting more direct sound deeper into the room, before we sort of activate or energize all that reverberant sound. We didn't send sound up right directly from the speaker. It has to hit something down here and bounce around a little to get up into the space. So we get the direct sound higher than reverberant sound just by choosing a speaker with a very high directivity, very tight directional control. And this is voice band only. Obviously, this doesn't have any deep bass to it. This particular model goes down to about 200 hertz. Now, if we take that same traditional cathedral and try to accomplish contemporary worship, we're going to have some problems. Deliver good articulation, the music system will need the same high directivity I just showed you, the speech system. Also, do not over-energize the bass. Low frequencies will mask the mids and highs. So it has to stay, well balanced at the rear of the room in order to maintain any kind of intelligibility. Use silent stage techniques. The E-drums, in-ear monitors, E-drums, guitar amp emulators, or stick the guitar amps in a back room and close the door and put a mic in front of them. Bring that out. People do that sometimes. Vibration transducers for the bass and drums, particularly the musicians who are used to sort of feeling their music and get better inspiration by feeling that vibration, even though it's not happening acoustically around them. They feel it, bone conduction on standing on a vibrating platform or a vibrating drum throne. If you have a loud stage sound like a typical rock and roll, you will simply overwhelm the whole room and make sound reinforcement pretty much impossible. You turn the PA system off and it's still too loud everywhere. So how about acoustic treatment in the traditional cathedral? Making a significant change to the acoustics in a cathedral is difficult and expensive. It will require a large quantity of acoustic material. It will be visually undesirable, most likely. And it may not even be legal if it's a historically significant edifice. If it's on a historic registry, you can't make certain changes. Now, the fire marshal can make changes if it has to be, but unfortunately, but a little sore spot with me. But you can't make visual changes to the room. So in that case, if you're having to do traditional contemporary music in a traditional cathedral, you gotta learn to deal with the acoustics. It can, by the way, be a very wonderful worship experience if the congregation can be heard singing and so forth. So the opposite end of the spectrum, we got office, retail, reclaimed space. Young growing churches find unoccupied retail and office space to be an attractive option. It's low cost, plenty of parking, flexible layout. You can just put walls wherever you want. Single level, fully accessible, no elevators to maintain. It's familiar, and it's not churchy. Some churches ministry is to people who wouldn't darken the door of a traditional church for various reasons. These buildings have low ceilings. The acoustics are often dry. They often have an acoustic tile ceiling in them already, which you can keep or remove. If you're using a larger amount of area in there, it often requires delayed speakers because the ceiling is too low to cover. You simply can't get a speaker high enough up front to cover front to rear from a front location. So if you're trying to do this reclaimed space with traditional worship, well, the acoustics are too dead. It doesn't have an organ. You can have an electric organ. Too little cubic volume. The racing guys say there's no substitute for cubic inches in your engine, and there's no substitute for cubic feet in volume when you want reverberation. You can substitute an acoustic enhancement system, such as the Lexicon layers, Meyer Consolation, and maybe some others. But they are very high budget. You know, if you got that kind of budget, well, it can be done. But it'll still lack the visual majesty of a cathedral. But reclaimed space for contemporary worship can work very well. Particularly if acoustic support of the congregational singing is not a high priority. If you've got a congregation that likes to sing and likes to hear themselves sing, yeah, then it may be too dead for them. But typically in contemporary worship, the people in the congregation aren't singing out that they necessarily hear themselves. In fact, some like it to be loud enough so that they can't hear themselves sing because they can't sing on key. All right, whatever. You know, it's different churches for different styles. A line array module mounted tight to the ceiling is a good option because they have narrow vertical pattern and freedom from reflection off the ceiling. If you think about a reflecting surface is actually a mirror image of another speaker just like it on the other side of that surface. So line array modules are meant to be next to each other in an array, obviously. So it's designed not to have a problem with that speaker next to it, so it won't have a problem with the reflection off the ceiling. This may require custom mounting hardware. I did this in a church, and it's obviously it's acoustic tile, so the reflection is not real bad anyway, but those are line array modules used singly. As obviously we've got left, center, right in front of the band, a right speaker for the screen playback and a delay halfway back. Posts are also a bane in these kind of spaces that you can't get away from, but this is an office space. A retail space would have a higher ceiling and the posts would be a little further apart. Acoustic treatment in a reclaimed space. Well, typically what you'd want to do is make it more live. A simple way to make it more live would be to replace the drywall tiles, replace the acoustic tiles with drywall tiles. Either the whole thing or partial, maybe part of an area, not another area. You could do it in random and checkerboard pattern to get some diffusion. They can also be made more live by removing the ceiling and blacking out the metal deck. Just paint everything up there black. It gives you more volume, more cubic volume because you're using that space. And hard surfaces, typically that's going to be a metal deck in the modern construction. If you do that, you need to be aware of noise issues, both from the mechanical equipment up there and also from rain. You'd be amazed how much sound rain makes falling on the roof when you don't have that extra space and the false ceiling in between to block that sound from coming down into the room. So if you're thinking of doing that, you need to, investigate those situations before you make a final decision. Worship styles in the sound system. Traditional liturgical Christian music is usually acoustic, piano, organ, light instrumental enforcement, maybe through the main sound system or sometimes an alternate system. Audience is reverently quiet, attentive, speech only, moderate levels are sufficient. Contemporary Christian can go up to full theatrical production. You've all seen that. Mega churches, rock and roll levels to 110, which isn't Christian, maybe, if depends on how you feel about that. The majority of churches are blended worship, somewhere in between that. The other thing to keep in mind, worship style is much less dependent on denominations than it was 40 years ago. When I first got into this building, I could look at the sign out front, note the denomination, and know pretty much what went on inside. That's not so much the case these days. So you need to find out what the client does and what he needs to do, what his needs are. Here's a couple of pictures, example churches we've done. This is a church that actually looks, it's a lot like a high school auditorium. You'd think, looking at the room, that might be just an high school auditorium. Ivy 6 line arrays, I believe 5 modules per side, and a little small speaker filling in the center because these arrays kind of miss an area in the front here, just a couple of rows. It's not a center per se for the whole room. It's just a fill for the very front of the room that's missed by the arrays. And here's an example of a stereo system. The speakers are kind of hidden pretty well there. There's a 3-element line array each side here, right in that dark spot they made so that the screens have good contrast. They hid some speakers in there. This is a left and right stereo system. Each of these arrays covers the entire room with side to side. So in this case, it wouldn't have been, I mean, we could have hung a speaker in the center. It would have gotten in the way of the visuals for the cross, and then it would have needed fills yet, and it ends up being about the same price. So that's good. Here's a church we just recently finished. In fact, I was up a couple of weeks ago to tune the system. An LVH system is a large venue horn. This is a 3-foot square for a 3-way horn. Bass, mid, and treble all feed into the same throat in the horn. Very high directivity, excellent cutoff from one side to the other. There's not overlap between them. Right down the center aisles, they cut off, and they good cut off to the stage. They don't throw sound up on the walls high, so it's a very good application of that system. Here's some traditional cathedrals. There are 3 speakers here. You see them? This is what they look like. That's a close-up of it. The line array tucked into the pole. There's one here. There's one here. There's one here, and there's another one off the screen on the other side. So that's an excellent example of hiding the speakers in plain sight. Everybody can, you can see them, you can hear them, but you don't see them. They're just not very visible. Here's another similar thing: loudspeaker tucked in among the beams. In this case, we added a little subwoofer up here on the post, just on the wall, to supplement it. This probably uses a little bit of music with this system as well as just a speech. And here's a similar system, another different architecture style, but again, the line array is tucked into the column. Here they have the transepts. You have a little speaker pointed out to the side to pick up the transepts on the floor plan off to the side. So thus ends my prepared presentation. Sounds about right time. There's my contact info, Dale Shirk at biamp.com. Biamp pays me to answer questions that you might have about which speaker to use, where to apply it, where to put it, where to point it. That's what application engineer is. So feel free to send me an email and discuss it if you've got some issues.
Thanks, Dale.
How does that work, Gene?
Yep, you can also send questions to me at glass@worshipfacility.com, and I'll either get the answers for you myself or send them on to Dale. I'm sure he could do a great job of answering whatever questions you have. Thanks again to Dale, and thank you for watching, and thanks to our sponsor, Biamp.